Let's take a look now at topic 19. We're going to construct confidence intervals for means. For those of you following along in your book, I'm on page 395. So back in topic 16, this was the first time that you saw the idea of confidence intervals, and we constructed those based on a population proportion. So now we're going to go back to that same idea of building a confidence interval, but in this case, we're going to deal with quantitative variables instead of categorical ones, which means instead of a population proportion, we're looking for a population mean. That implies now something else. We need a new probability model that's called a T distribution. And again, if you've got your calculator, we will explore that. All right, so for our first example, man did a bunch of research and wrote a book called Mindless Eating. There's a website, there's all kinds of tie-ins here. Why we eat more than we think. And oh goodness, if you're staying home, this is one of the myriad of things that people worry about. I'm just amused at the logo that they came up with there, the graphics for mindless eating. It's not a fork and a spoon, it's a pitchfork and a shovel. Did you notice that? Okay. One of the experiments that he conducted here involved a sample of 20 undergraduate students from the University of Illinois at Urbana-Champaign. They were asked to take as many M&Ms as they wanted from a 24-ounce bowl. As they walked in, there was a lab study session that day. Um, So, after picking the M&Ms individually, they determined how many M&Ms each person had selected. Suppose you plan to offer a study session, you need to know how much candy to bring, and therefore you'd like to estimate how many M&Ms students tend to take on average. So if we're looking for the number of M&Ms candies selected, that's a quantitative variable, okay? Based on that one little project there, here is the summary data. N is 20, the mean is 50.15, standard deviation is 30.31. There was somebody who only took 7. The lower quartile was 32.35. The median, notice again, median and mean don't have to be the same value. The upper quartile, and then, yes, take a look at that. The max, there was somebody, oh, look, here's a big bowl of M&Ms. Oh, you're going to give me my own bowl, take as many as I want. The person grabbed 111 of them. Wow. So we're talking about the 50.15, the mean, and the 30.31. Are those values parameters, or are they statistics? Well, in this case, they are statistics. Because again, it came from the sample. So the mean here, the 50.15, the symbol that we use there should be X bar. And then the 30.31 is the standard deviation here from our sample, and that's a lowercase Roman s. Okay. For part C, identify in words a suitable parameter in this study, and what symbol represents that parameter? Well, what we're looking for here is the average number of candies that would be selected by all students in the population, and in that case, we're looking for a population mean, so that would be the Greek letter mu. Part D, do you know the value of the parameter in this study? Oh, no, we don't. Well, we're guessing. I think it's a reasonable guess here to say the value is more likely to be close to the 50.15 than far from it. The sample means from random samples will cluster around the population mean. So if we could use the central limit theorem, that tells us the population mean should be no more than 2 standard deviations from any sample mean. As we've seen, you can form an interval estimate of a parameter by starting with sample statistics and go 2 standard deviations on either side of it here. So then for part E, do you know the value of sigma? Again, remember, that represents the population standard deviation. No. Again, here's one of the key issues. We're trying to come up with an interval, a confidence interval here to estimate what the population mean would be. But we don't know the value for mu. We don't know the standard deviation either. Um, a major drawback of using this procedure is that it requires you to know the value of the population standard deviation, which you almost never know. You know, if you knew the population standard deviation, isn't it likely you would also know the population mean? And then we don't need a confidence interval to estimate it in the first place. So for part F, a reasonable substitute for sigma that you can calculate from the sample data is S, our sample standard deviation. Okay, so this formula here for a population mean, this should look somewhat familiar, okay? What we had before was p hat, plus or minus z star, but now we're starting with x bar. Again, we're taking that same idea, the same basic formula that we had for a confidence interval for proportions, and now we're going to build it here for means. To estimate standard deviation of a sample mean x, we're going to replace the population standard deviation, which was sigma, with the sample standard deviation s, giving us, now here's one of the new terms you need to know, standard error. So not standard deviation, okay? So again, there's a similarity here between this fraction and this fraction, okay? Instead of the population standard deviation sigma, we're going to use the sample standard deviation. And to distinguish between the two, we're not going to call this standard deviation. We're going to call this the standard error for the sample mean. So if we go through and calculate the standard error in this case, we're going to use the sample standard deviation, which they told us in that previous chart was 30.31. We're going to divide by the square root of n. Our sample size in this case was 20, so that'll give us a standard error of 6.7775. Again, if we go to 4 decimal places. So for part H, add and subtract 2 standard errors from the sample mean to form an interval estimate for the population mean. All right, so if we go 2 standard errors, add that to the x bar, the sample mean of 50.15, take the 50.15, subtract 2 times the standard errors. This will give us a confidence interval. So, on average, people will probably take somewhere between 36 and 64 candies, M&Ms. So this is one way of finding a confidence interval for a population mean, but oh my goodness. All right, it took us to step H in the problem to finally get a confidence interval. But as we said before, we're not quite using the same normal distribution that we did with the z values. Now again, this is a chart um, that you could find on page 401 if you're following along in your book there. The one that goes the highest is the z-scores, the normal distribution. Those are for proportions. In the development of statistics, somebody got a little bit curious about if we treat a proportion and a mean the exact same way, there were errors that popped up. So doing further investigation, somebody discovered when it comes to means, again, based on quantitative variables, it's not, oh, it looks so similar, doesn't it? But it's not exactly the same. And depending upon what it is that you're trying to calculate here, for a very, very large sample size, well, that difference in the shape there can make a big difference. So we have the normal distribution there that we got with z-scores. T-scores are what we need to use here because it's a sample mean we're trying to use. And if you have a Texas Instruments calculator, this is going to be not a problem. If you don't have a Texas Instruments calculator or something else that will do statistical functions programmed in, technology is not going to be kind to you, but there's a way around that. Okay? Yeah. Okay. So confidence interval for a population mean, here's our real formula. Okay? So instead of Z star, that critical value, we need T star now. This is the appropriate critical value from the T distribution, not the Z distribution. Again, before we can apply a confidence interval, we have two technical conditions that must be met. First of all, it has to be a simple random sample from the population of interest. That's the exact same thing that we had with confidence intervals and with our test of significance when we were dealing with a population proportion. And either the sample size has to be large enough, so it's got to be 30 or more, or we're told that the population is normally distributed. Okay, so again, for the population proportion, there were two technical conditions, and with that second one, you had to do a little bit of multiplying to make sure the sample size was large enough for both P and 1 minus P. Here, you either have to have at least 30, or you're told that the population is normally distributed. Okay, no calculations needed with this one here. So if we go to page 403, state and comment on the technical conditions of the validity of a one sample T interval with this data. Not all that confident. Sample must be a simple random sample. Well, okay, the students that showed up to the lab review that day, we weren't told how the sample was selected. Um, so can we safely say it's at least representative of the population? But the sample size is too small. Um, if you looked in the book there and saw the distribution there, it doesn't appear to be a symmetric distribution. So we've got a little bit of a doubt that the population distribution would be normal. But if we proceed anyway, they ask you, top of page 404, calculate and interpret a 95% T confidence interval for the parameter of interest. Make sure your interpretation is in the context of the study and clearly describes the parameter and the population you're willing to generalize to. Okay, so what you see on the screen right now, for those of you that have been able to acquire a TI-84 Plus, okay, second row down, adjacent to the up, down, left, right arrows, there's a button that actually says Stat, Statistics. And then we want to get to the test menu, so you can either push the right arrow twice or the left arrow once. And then we've got to scroll down to option number 8, a T interval. Okay. Once that pops up, you've got the option here of how you're going to input the information. Well, we're not going to input all of all right, this person took 7, this person took 22, this person took 111. We don't have all that information. We have the summary statistics. So you should right arrow to get the stats highlighted there. And then we input the data that they gave us. Again, the X bar, the mean is 50.15. The sample standard deviation was 30.31. There were 20 people, and we're looking at a confidence level of 0.95. Okay, for those of you that have, where'd my, yay, the Nspire, okay, this is very, very similar here. Push the menu button. Then we're going to go to number 6, statistics. This is just so simple here. We're looking for a confidence interval. And then option 2 is the T interval. Now again, they give you the same option here that if we had the data, we could just use that, and oh my goodness, the things that it does in a heartbeat is amazing. But in this case, we have these summary statistics, so we need to change that. And again, type in those values there that we had of, no, I've forgotten them, 50.15, tab, 30.31. There were 20 people. We got the right values here. 50.15, 30.31. Okay. Click OK. And oh my goodness, there's a whole mess of stuff here that we'd have to then take a closer look at. These two lines give us the confidence interval. Okay, C lower, C upper. That's the part that you need to pick out. Okay, so again, here was the 50.15. That's the X bar that we put in. This is an interesting thing here. DF is 19. Now, for those of you that don't have the calculator, I'm sorry, I've tried looking. Desmos does not do this. other online calculators. Oh my goodness, it's so tedious to build it up here. So let's talk about that DF. This is a term invented again by statisticians several years ago. This is called degrees of freedom. That's a term that you need to know. If you don't have the calculator here, how are you going to create this interval? The calculator does it just in a heartbeat. We could go through, all right, we know the summary statistics, we know what X bar is, we know what S is, we know the sample size. The issue here is T star. How do we find that critical value? If you flip in your book, there are several appendices in the it's not the very last page. There's an index that takes up the last 7 or 8 or different pages. Right in front of the index, there's a section of tables. I believe at one point in time we may have looked at table 1, which was just random digits. I think I made you one day in class look at table 2, the standard normal probabilities. But if you don't have a calculator that'll do this for you, you need to look at table number 3, and I snapped a picture of it here, the t-distribution critical values, because the value there of t star doesn't just depend upon one thing, it depends upon a combination of two. So again, with what we're talking about on page 404, a 95% T confidence interval. So that means we'll look here at this column here says 95. So we're going to read down here. But notice on the left-hand side here, the other line that we need to pay attention to on this chart, on this table here, are the degrees of freedom. In this case, in this topic here, degrees of freedom is a very simple thing where you're going to take n minus 1. So in this case, they had 20 people who participated in this little experiment here. So if we take 20 minus 1, that means that's 19 degrees of freedom. So we find the 19 here, we read across, and where those intersect, that's your critical T value. So we go back to our lovely little formula right here. So now, again, doing this by hand, the 50.15 was X bar, the 30.31 is S, N is 20, and your value for T star is right there in the table. Sorry, don't know why it ended up down here. 2.093. It's not going to be that same value with every single problem here. The degrees of freedom will change depending upon the sample size. So that's why we're not going to be able to, like we did with the z-star values back in the, I guess it was 16, when we did confidence intervals for a proportion. We could figure out what that z-star was going to be for 95% confidence every single time, for 90, for 99. It didn't change. Here it changes. Okay, so you just basically got to get used to that. Okay. Okay, so now that we've got that all figured out, So 95% confidence interval here, blah, blah, blah. They're walking you through the tedious little calculations, again, that you would need to know. Okay, so again, if you're using that table, here's the 2093 that we just found. Okay, plug those numbers in. Again, add and subtract to build our confidence interval. And again, our interpretation in context. We're 95% certain that the average number of M&Ms that would be selected by all students in all the study sessions taken at random is somewhere between 36 and 65 candies. Make sure you buy enough. All right, so then part C, what does that phrase 95% confidence means? If we were to repeatedly take samples of size 20 and construct t-intervals in this manner, in the long run, 95% of those intervals would contain the value of mu. How does this interval compare to the informal interval when we took 2 times the standard error? Well, okay, we compare here. I'm sorry, let me highlight things. Nice if we cooperated here. And this. You know, they're not that much different because, again, we took 2 times the standard error. In this case, we're taking just a small bit more than 2 times the standard error. So yeah, those are very, very similar. One of the key things, they have the exact same center, okay? But the t value here, calculated here, is slightly wider because our critical t value was a little bit bigger than that rough empirical rule estimate of just using 2. Now, what if we want a 90% confidence level? Okay, so again, with your calculator, it's not that tough to go back and change that. For a 90% confidence level, with your chart here, you just read a different column. That'll get you a different T-star value. And then the next thing they want was a 99% confidence interval. In this case, it's the same sample size of 20, so you're going to use that same row of 19 degrees of freedom. Okay, so now let's compare here. 90% confidence level, 95% confidence level, and a 99% confidence level for our confidence intervals. Which one's the widest? Yeah, the 99. Okay, we're 99% certain that if we did this experiment over and over again, this interval would capture the actual value there of mu. Which one's the smallest? Yeah, the 90% confidence interval is the smallest one, most closely centered around the mean of the 50.15. Now, here's a key thing. For part I, suppose the sample size had been 200 instead of 20. But the sample distribution of the number of candies had been sharply skewed. Would this t interval calculation still be valid? Yes, it would, because again, our minimum there of basically using our central limit theorem, in this case, our sample size should be greater than 30, and oh my goodness, 200 is definitely greater than 30. So if we change those values, again with calculator technology, that's pretty simple. With an sample size of 200, you'll notice from the table of values there, it does not go down to 200. Um, please note, look at how narrow those confidence intervals are. They all have the same center, the same midpoint as everything we just did there for part H. But because the sample size is so much bigger, the denominator in our standard error got much, much smaller. So our confidence interval here is very narrow compared to the original. Okay, let me walk you through here. We're going to skip a few more of those things because, yeah, we're not there to collect the data to ask you how much you slept last night. So we're going to go to 19.6 backpack weights. If you remember back, it was first brought up in topic 2, and then we came back to it in number 10. Student researchers recorded body weights and backpack weights for a sample of 100 students on their particular campus. Okay, so the observational units were the students. The variable is ratio of backpack weight to body weight. If we come up with that ratio, it's going to be a quantitative value. So the sample is the 100 students from the campus where they collected the data, but the population is then generalized to all the Cal Poly students at the time that that study was conducted. For part B, if we use the data that's available to you online, we could create the ratio of backpack weight to body weight variable for each student. And yeah, okay. Well, you guys don't have access to that, so you're just going to have to trust me. The mean is 0.077. The 5-number summary there. Students in the sample carried as little as 1.6% of their body weight in their backpacks, and it went as high as 18.1% of their body weight in their backpacks. Standard deviation, again, that's not in the 5-number summary, but the standard deviation there is 0.037. Okay, and again, that's not stuff that you're supposed to be able to calculate on your own without the data itself. So if we pay attention here to the mean and the sample standard deviation, for part C, they challenge you to come up with a 99% confidence interval for the population mean weight ratio. Okay, so again, they told us the mean, 0.077. They told us the sample standard deviation, 0.037. There were 100 students that were involved in this little experiment here, and they're asking for a 99% confidence level. Plugged it in the calculator and boom. Okay. So for Cal Poly students, on average, the weight of their backpack to their body weight ratio is going to be somewhere between 0.0673 and 0.0867, and we are 99% confident that other samples taken would produce the correct ratio for the entire population. All right, So that wraps it up. Take a look at your assignment here is all the parts. Sorry, we can't do a lot of the initial ones there because you need all of the raw data given to you. Make sure that you take a moment and read through page 411, the wrap up, and then the in brief that's continued there on page 412. But then the first problem I want you to try and work out is number 11. There's parts A, B, C. You should be able to do all of those. Then go to number 16. There's a few parts there. You should be able to deal with all of that. 17, they give you the data there. It looks longer than it really is. Part D is really, really long, and they're asking you which of these are reasonable interpretations. So it's a lot of reading, not a lot of calculating. Don't freak on me. Then go to number 22. You can skip parts A and B. Just do C and D. And then 23, you should be able to do all of that. Good luck.